Hi, everyone. I'm Owen,
And I'm Nimah.
and today we'll be talking about cryogenic electron microscopy.
So our story today is going to start with the G protein coupled receptors, or GPCRs. They're a group of membrane proteins in the human genome that sit on the surface of cells and translate outside signals into internal actions. So they're clearly very important. However, imaging GPCRs was considered one of the hardest problems in structural biology. In 2000, the structure of bovine rhodopsin, which is a type of GPCR, was discovered using X-ray crystallography. As you can see here, this is the X-ray diffraction image. And closer to 2007, we were able to determine the crystal structure as well. However, more recently in 2019, using cryo-EM density maps, we were able to understand a more comprehensive structure, as you can see to the image to your right. So before I talk about cryo-EM specifically, let's talk about what necessitated the invention of cryo-EM in the first place. So many of the imaging techniques in the past had a few problems or constraints that came with it. So for X-ray crystallography, for example, some of the molecules were too flexible or complex to be imaged. It also required a perfect crystal to be formed in the sample, which can be hard to do. And it also doesn't capture the motion of compounds. Or you can't determine the motion of compounds using this technique. For NMR, some of the molecules were too large to be imaged, and it also required a high concentration of the compound, or at least higher than you would need in cryo-EM today. And for transmission electron microscopy, or TEM, it often required harsh chemicals to prep the sample, which can destroy or distort the sample in the first place. It also uses vacuum, which meant that the sample must be completely dehydrated, which can be difficult to do. And it also provided only limited resolution.
So the first step in making the sample is the flash freeze process. So the sample undergoes vitrification, which is rapid freezing in less than 100 microseconds in cryo-electron microscopy. As you can see in the image to the right, you have this foil mesh, which is made from a carbon gold grid for sample application. Here we see our sample is ribosomes in a liquid, and that is trapped onto the foil mesh. It's plunged rapidly into the liquid ethane, which freezes it almost instantly. And this liquid ethane is the most commonly used cryogen at a negative 183 degrees Celsius. However, because cryo-EM is still such a new technology, people are constantly looking at how to improve it, how to change it, and what aspects of the procedure can be improved upon. So in that case, some people have been testing propane and have had varied results on potential high freezing efficiency, better than liquid ethane. Why is this so important? Well, it creates amorphous or glass-like ice instead of crystalline ice. So in the first image, we can see the difference between a crystalline solid and an amorphous solid. Most ice exists in a crystalline hexagonal LH formation, which necessitates this very rigid hexagonal structure. Everything is where it's supposed to be, everything's bound together, whereas this amorphous solid has disordered and randomized molecular arrangements. One of the ways that it was described in one of the articles that I read was amorphous ice is like a liquid that has lost its ability to flow. On the right, we can see how the increase in amorphousness or the increase in the disordered and randomized molecular arrangements within these blocks of ice increase its ability to withstand shear at a higher shear rate. When you take snapshots of this amorphous ice, it looks like a liquid, which allows for this retention of this biological conformation instead of, as what Nimah was talking about, sample destruction through different processing techniques.
So in order to read the data, so the most common, I guess, form of cryo-EM is using transmission electron microscopy. However, the same cryo-SEM or using scanning electron microscopy also does exist. However, it's a lot more niche for specialized cases. So we're not going to delve into that today. So TEM is the standard. Transmission electron microscopy is a high resolution imaging technique that transmits a high energy electron beam through an ultra thin specimen to create a detailed or very magnified image. It's widely used in biology, material science, for analyzing cells, viruses, and other nanomaterials. So the way that it works is that a beam of electrons is fired through using an electron gun through the vitrified layer. And the electrons get scattered in the sample. and then these scattered electrons are focused by the EM lens, thus creating a 2D projection, as you can see on the right image. One of the few constraints here is that although it does offer a much higher resolution than a light-based microscope, which enables an atomic level detail, you need a very thin sample, usually around 100 to 200 nanometers, in order for the electrons to pass. So to actually analyze this data, cryo-EM creates these 2D projections by transmitting these electron beams through this vitrified specimen, which results in an image that is a 2D projection or a summation of the 3D object or the sample along the beam path. So it uses Fourier transforms to analyze these projections, as this 2D projection corresponds to a central slice within the 3D Fourier space. So as you can see over here, what's really happening is that you have the image on this 2D projection, and you can achieve this image at different angles. A Fourier transform is applied to it, which creates this more like circular image. And then using the Fourier slice theorem, it's able to convert these into a 3D slice. And once you get enough of these slices through getting images in various angles, you're able to put these slices back together to give you the sample of choice and really get the 3D image of the object.
So today I want to talk a bit about some of the advantages of cryo-electron microscopy. So on the left, we see the scanning electron microscopy of ribosomes in 1963, when the technology was first becoming prevalent in modern science. And on the right, we can see the cryo-electron microscopy of ribosomes in 2009, right, when electron microscopy, cryo-EM, was really hitting the mainstream. Cryo-EM enables the visualization of biomolecules in a natural hydrated conformation and incorporates advancements in technology and imaging software to increase resolution. We can see a marked difference in these two photos. And while there is a time lapse, we see on the right, on the left, it is the very beginning of SEM, whereas on the right, it's kind of the beginning of cryo-EM. And it's only gotten better since 2009, in the past 15 years, as Nimah will touch upon later. They can also capture multiple conformational states of the same biomolecule because they're frozen in different arrangements, and then those can be examined. Minimal amounts of sample is needed, which is great because you don't have to prep and purify and aggregate a large amount of sample to get these results. However, some of these advantages can also turn into drawbacks. It requires homogeneity in particle population for high resolution, which essentially means that you want most of your enzymes or protein or whatever you're studying to be in the same conformation. If they're in different conformations, then those scans that Nimah was talking about, that you're trying to transform into a 3D resolution, are all going to be in different states. And so you're trying to put together this 3D rendered image of proteins that look different from each other, and that's impossibly hard to do. There's also some biomolecule size constraints where under 50 kilodaltons and over about 5 megadaltons, cryo-EM doesn't work anymore. It can't produce that level of atomic resolution that makes it such a good technique. There's also high costs involved, and technical experience is essential to producing results. People need to be trained on this for a long amount of time, and it's different from TEM and SEM in that it has these high level of costs. It requires extremely high sample purity, which I guess is in contrast to the low amount of sample needed. And there can be ethane contamination, which is during the vitrification, the flash freezing process, a small amount of ethane resides and remains on that carbon gold foil. And that leaves these dark shadows, which overlap with the sample images and make it really hard to read. It essentially destroys the sample.
So before 2013, you could only really see quote unquote blobology or the general shape of a protein. In the past, what was used to capture these images was either film or charged coupled device cameras or CCD cameras. So these cameras use scintillators, which are indirect detectors. Basically, the way that it works is that the electron beam passes through the sample, it hits the scintillator, and it produces photons, which is guided to the sensor using the fiber optic coupling, as you can see over there. So the issue here is that in this older CCD technology, because you need the scintillator and it would convert it to light first in order to image, it would cause a lot of lateral light scattering, which would just mean that you would have blurred images in the end. What we do now, since the 2013 resolution revolution, is we use direct electron detectors. So these use primary electron beams to strike the sensor directly. The method that it uses is the electron counting mode. So basically what this does is high-speed sampling, which just means that the sensor is read out thousands of times per second, which is fast enough that each frame likely contains either 0 or 1 electron per hit per neighborhood of these pixels. Then it does a thresholding, which is that the electrons identify discrete clusters of charge that exceed the background noise. It does a centroid reading, which is basically where this primary electron hits the center. When that happens, the resulting charge may spread across a grid of pixels. The camera's hardware is able to mathematically determine the center of this grid, which is good because using the next step, which is digital integration, the software is able to record a peak or a specific digital signal at that specific coordinate, and then discard the remaining cluster data, which basically just eliminates the variations in the amount of charge deposited by electrons, which means you get minimal scattering and minimal noise, and you get very high resolution readings. And this is what led to, as you can see in the past, these more just like general shape of proteins to a more specific image of what they look like.
So now we're going to look at some current applications of cryo-electron microscopy, which is mapping these neurodegenerative amyloid fibrils. So Lee, Bevanchak, and Sherwitz at Case Western Reserve University in 2021 used cryo-electron microscopy to map cross-sections of amyloid fibrils. These are key to understanding the structure and formation of amyloid aggregates in several different neurodegenerative diseases, such as ALS, Alzheimer's, Huntington's. And the image on the right is looking at some of these cross-sections which stack on top of each other in these aggregates. Fibril coupling they found, well, they built off of atomic force microscopy, AFM, and they presided a more natural conformational state, and they looked at pH-dependent morphologies. So fibril clumping was pH-dependent, they found, where depending on the pH levels, as they increased the acidity, they saw different twists and turns in the formation of an alpha helical or just a helical format of these amyloid fibrils. And so their work in mapping the structure of neurodegenerative amyloid fibrils is critical for understanding how these aggregates and these plaques form in the first place. And so through their work, they looked for what can cause these conformational changes and how we can potentially prevent these conformational changes. We have some future developments in cryo-electron microscopy technology as well, which is looking at cryo-TREM or cryo-time-resolved electron microscopy. This uses C-SPAN, which is cryo-electron microscopy sample preparation with a light-activated molecule. What this allows for is that different biomolecules have times on their conformational changes. They change over periods of time, whether that is nanoseconds or whether that is minutes. And so being able to understand how fast these changes happen and being able to account for that in your cryo-electron microscopy is very critically important. So this team that was working on it developed a slow and fast cryo-EM testing method, which uses a photoreceptor attached to the grid. Essentially what happens is they turn an LED on that activates the photoreceptor, and then that activates the conformational change or the reaction that this biomolecule is undergoing. And through this, in the slow, they turn the LED on, and then they can wait a certain amount of time called the plunge delay before they plunge the grid into the liquid ethane. Whereas with the fast, the LED on happens very, very last. And that allows for even resolution after a couple microseconds of activation. And so through this, you can make a time course of biomolecules and look at how they change over a period of time, which is very important in understanding how they change, how they move within our cells and within our bodies.
So the reason we're talking about this today is because cryo-EM won the 2017 Nobel Prize. Yay! So before this innovation, electron microscopy was thought to only work on dead or dehydrated matter. And so X-ray crystallography and other techniques required forming complex or often impossible crystals of proteins. So cryo-EM has really helped scientists to study molecular machinery in its natural state, which is huge. So the three winners, one of them, Jacques Dubochet, I might be butchering these names, I'm so sorry, introduced the rapid vitrification technique in the 1980s, which Owen talked about. Joachim Frank developed the image processing software that is able to generate these sharp 3D images from the more fuzzy 2D projections. And Richard Henderson was able to image bacterial rhodopsin in 1990, which was one of the first near atomic resolution images of a protein, as you can see at the bottom here. So yeah, that's all we have for today. These are our references, and thank you for watching.
Thank you for watching. Let us know if you have any questions.